Hello students, welcome to EPG Pathshala. I am Dr. Savita Sharma from University of Delhi. Today we are going to learn in this module about squid under the paper Thin Film Science and Technology. So students, let us see what we are going to learn in this module. First of all, we'll have a brief introduction about squid. Then we'll study in detail about the working principle of squid. Then thirdly, we'll study about the squid sensors, their operation and maintenance. Then fourthly, we'll study the different types of squid sensors, mainly the two types, RF squid and DC squid. Then fifth, we'll see about the various application areas of the squid devices. Then next, we'll compare the two types of squids, that is the RF squid and DC squid, and we'll see their positive and negative points. Then in the end, we'll study the limitations on squid technology. Before learning in detail, let's have a brief introduction. Magnetic fields and their properties can be measured by so many ways, among which induction coils, magnetoresistive magnetometers, Hall effect, magneto-optical magnetometers, and optically pumped magnetometers are frequently used sensing methods. The sensitivities, the range of the sensitivities or the sensitivities of these sensing methods lies from picotesla to microtesla levels. Out of all the devices, superconducting quantum interference device, which we called as SQUID, is considered as the most sensitive magnetic flux detector. The field resolution of SQUID devices is 10 to 17 Tesla. The device can be operated at low temperatures such as cryogenic temperatures with quantum limited sensitivity. In the development and commercialization of ultra-sensitive electric and magnetic measurement systems, superconducting quantum interference devices or SQUIDs have been considered as a major factor. Many of the cases, no methodology works top measure magnetic properties other than SQUID. In the present module, we examine the main features of developing, constructing, and operating SQUID measurement systems. Materials used to fabricate SQUID sensors with the various types of SQUID sensor description as well as the operating principles and the properties are listed below. Most of the applications of the SQUID sensors are based on lower frequencies. However, they can be operated well above 1 MHz frequency. Different detection coil configuration for the manufacturing of SQUID sensors and various applications in the area of environment, medicines, etc. are described. SQUID devices. SQUID device is the most fundamentally used application of flux quantization and Josephson phenomena. Therefore, before going into the depth analysis of SQUID's devices, let us first understand some basic terms. The first basic term is superconductivity. H. Owens in 1908 measures the electrical resistance of metals at very low temperatures by successfully liquefying helium. In 1911, scientists discovered that as the temperature of mercury was reduced at around 4.2 Kelvin, the resistance of mercury did not fall continuously as expected, but in its place dropped suddenly to zero over a range of a few hundredths of a degree. This phenomena of non-zero resistance of a metal was termed as superconductivity. Later on, the same phenomena was also discovered for other metals such as tin, lead, and aluminium at critical temperatures lying between 4 to 10 Kelvin. However, the microscopic mechanism of such an unexpected behavior of the metals found at some critical temperatures, known as superconductivity, was not discovered until 1957. In 1957, three of the scientists, Bardeen, Cooper, and Sheffer, tried to investigate this microscopic behavior. In 1933, Meissner and Oskensfeld was also discovered another important property of superconductors called Meissner effect. Superconductors exhibits the property of perfect conductivity such that the magnetic flux should be excluded from entering a superconductor, whereas it is also found that when the superconducting material was cooled below its temperature of transition, the magnetic flux was expelled from the interior of the material. This phenomena is known as Meissner effect. Now let us discuss this effect called as the Meissner effect. In the presence of the magnetic field, when a superconductor is cooled through its transition temperature, a distinct property is observed. When a non-superconducting material is placed in the magnetic field, the magnetic lines of flux penetrate within the material, which you can see in the given figure, figure 1, in the A part. In a perfectly conducting material, to prevent any change in the magnetic field in the interior of the conductor, an induced current is produced within the conductor. On the other hand, for superconductor, the magnetic flux lines exist only for a shallow surface layer called the penetration depth and are not present within the superconducting region. The magnetic flux is excluded from the conductor when it becomes superconducting, whereas the flux traps in the interior of a perfect conductor as shown in the B part of the given figure 1. This essential quality of flux expulsion of the superconductors is called Meissner effect. In case of a continuous solid, the flux is expelled out of a superconductor, whereas it is trapped in the interior of a material if it forms a ring. You can see this in the B part of the given figure. A current is induced around the ring to keep the magnetic flux inside the ring constant when the magnetic field is then turned off. You can see that the state of persistent current in C part of the given figure. So in the given figure 1, you can see in the presence of an external magnetic field, a superconducting material shows the Meissner effect. Let us now discuss about flux quantization. The magnetic flux is trapped within a superconducting ring until it is in the superconducting state. Some extraordinary properties are shown by this trapped flux. Firstly, the intensity of the magnetic flux cannot be changed in the superconducting ring, and only discrete levels of the magnetic flux can be trapped as shown in figure 2. Thus, we can say that the magnetic flux exists in the form of the flux quantum and is said to be quantized. Figure given here shows the quantization of the magnetic flux. Now let us discuss about the Josephson effect. The Cooper pair wave function of a superconducting wire interrupted by a normal region would quickly decay across the resistive barrier, and the resultant superconducting current would die down as shown in the figure 3. The electrons can tunnel through the junction of two superconducting regions separated by a resistive barrier. This possibility of tunneling of electrons is given by Josephson in 1962. Josephson junction describes the contact between two superconductors in which there is found to be a thin, that is less than 2 nanometer, dielectric tunnel barrier between the two superconductors. The effect explains the tunneling of Cooper pairs through the barrier. The DC Josephson effects relates the tunnel current to the critical current through a Josephson junction, as the equation which shows this is I is equal to IC multiplied by sin phi, where IC is the critical current. The maximum Josephson tunnel current flowing through the barrier is called the critical current. The value of the tunnel current is measured by the density of Cooper pairs, tunnel barrier thickness, area of the tunnel junction, and by the phase difference. The AC Josephson effect relates the voltage across a junction to the temporal change of the phase difference. Thus, a voltage across a Josephson junction leads to a current. So, the given figure here shows the decay of a wave function across the resistive barrier between two superconducting material junction and the measured current across the junction versus voltage curve of a Josephson tunnel junction. So now discuss about the superconducting quantum interference devices or the SQUID working principle. The figure given here shows the SQUID loop dual junction. What is a SQUID? SQUID is a superconducting ring of intermittent by one or more Josephson junction and used to measure very small variations in magnetic flux by utilizing Josephson effect phenomena. The operational point is marked on the IV curve midway between superconducting and resistive behaviors, and the corresponding bias current is applied. We can see this curve in figure 5. The hysteretic behavior of the IV curve is prevented by putting the shunt resistors. The inductively coupled magnetic flux creates screening currents in the SQUID loop, which depending on the direction of the induced flux either increase or decrease the output current. The bias current is fixed at a little higher value than the output current. The SQUID can be locked at a unique point on the voltage flux curve by using the external feedback electronics, and thus the feedback current is also measured with the help of externally applied flux. The steepest part of the voltage flux curve having maximum value of V by psi is the appropriate portions of the SQUID's operation. Figure 5 here shows in the A part Josephson junction bias point, and in the B part of the figure you can see the V psi curve shown at constant bias current. Now let's move to the topic SQUID sensors. So first of all, let's discuss about the materials. Among the materials, first of all, let's study about the low temperature superconducting materials, which are also called as LTS. LTS materials are metallic in nature. They shows isotropic behavior. They are chemically stable in air and found to have large coherence lengths, which is found to be tens to hundreds of interatomic distances. Although at liquid helium temperatures, some non-metallic and organic compounds have been found to be superconducting, but none of them is used to fabricate SQUID devices. On the basis of the unique properties shown by these materials, three-dimensional structured devices can be fabricated by using LTS materials. Thus, crossovers, multilayer structures, and multi-turn devices can be made over single-turn devices which offer higher sensitivity. The next category is the high temperature superconducting materials, or we can call it as HTS. HTS materials are ceramics in nature having brittleness, shows an anisotropic behavior with planar geometry. The coherent length of the HTS material lies in the C direction, that is considerably small in dimension. Larger dimensions are required by the HTS crossovers, which are needed for the multi-turn coils, and thus a significant 1/f noise is introduced due to the formation of a Josephson or insulating junction. HTS structures are degraded very fast in the presence of the moisture, which adds another disadvantage to it. The next part in the squid sensors is the flux transformers. The area of the squid detection loop is very small, and also inductance, that is of the order of 10 to the power minus 10 Henry, is associated with it. So this is the major problem faced in using the squid detection loop. On the other hand, the sensitivity would be increased by increasing the area of the loop or connecting a larger loop in series. However, increased inductance of the larger loop produces the impedance mismatch, which cancels out the sensitivity gain majorly. Multilayer flux transformer is used by most of the LTS squid sensors to couple an externally detected flux into the squid loop, which you can see in the given figure 6. The given figure 6 shows the external flux coupler flux transformer, that is two turn detection coils. One you can see the squid loop, another is the input coil. Then the third thing which we are going to study under the squid sensors are the fractional turn squids. By connecting a number of single detection coils in parallel, not in series, as in case traditional multi-turn coils is found to be another way to increase the sensitivity of a bare squid loop. You can see this in figure number 7. The fundamental concept behind this thought is to have a large area for coupling to an external coil by keeping the inductance of the squid loop itself very small. So the figure 7 given here shows in its A part the parallel turn squid sensor and in the B part fabricated device. Now let us study the operation and performance of the squid sensors. On the basis of the operation, squid sensors are divided into two broad categories. The first category is the RF squid and the second category is the DC squid, or the radio frequency squid or the direct current squid. So let us first study in detail about the RF squid. Single Josephson junction is used in the fabrication of RF squid, where input coil is inductively coupled with the squid loop and flux is thus induced. The coupled input coil is thus joined the squid loop to the electronic circuitry and to the RF coil, which becomes the part of a high Q resonant tank circuit, which measures the corresponding squid loop current changes. A constant current radio frequency oscillator is used to driven this tuned circuit, which also couples squid loop weakly to it. The output of the RF amplifier increases with the increase in the amplitude of the oscillator until a critical level is reached. Here you can see the figure 8, in which there is a block diagram showing the locked loop operation of a RF squid with squid input electronics. You can see the cryogenic region in it consisting of the input coil and the RF coil. where there is a weak link between them. Then you can see the RF oscillator, and there is an amplifier and integrator comprising the other circuitry. The second type is the direct current squid or the DC squid. In case of a DC squid, squid loop is inductively coupled with the input circuit, feedback electronics, and modulation coils, and they are not wound around as in the case of the RF squid. Figure 9 shows the schematic of a DC squid. The squid loop is biased with the DC current, that is the direct current, which is about twice to that of the critical current, and thus a DC voltage is developed across the junctions. A wave function phase change is introduced or induced due to the change in the magnetic flux linked with the squid loop, which increases the current through one Josephson junction and decreases the current in the other. With the increase or decrease in the external flux, the voltage will change in a periodic manner, having flux quantum as period. It shows the figure 9, in which you can see the DC squid block diagram, in which instead of using the RF source, there is a DC current source. Again, there is an input coil and the mod coil in the cryogenic region, and there is other modulation oscillator and integrator giving the feedback current. Now let us compare the radio frequency squid versus direct current squid. Direct current or DC squid offers much lower noise as compared to the RF squid. Secondly, DC squid is more sensitive than RF squid. However, this increases the electronics complexity requires to operate DC squid. That is, being DC squid being more sensitive, we prefer RF squid because of the less complexity in circuit. Then thirdly, two nearly identical Josephson junctions in a single device is the major challenge in DC squid fabrication, whereas RF squid require only one junction. Then lastly, the early LTS development was performed with the RF squids. However, the first type of squid, magnetometer, was made using LTS DC squid. Now let us discuss the applications of squid. Squid devices are majorly used to identify very small amount of magnetic field, current, voltage, inductance, and magnetic susceptibility, etc. These devices show excellent sensitivity in the magnetic flux detection. The devices have been used to detect small quantities. These devices are used in the form of magnetometers and gradiometers. Now let us see the various areas of squid devices which are given below. The first application or the area of application of squid devices is MEG, which is magnetoencephalography. Weak magnetic fields are produced in the brain by the presence of the electrical currents occurring naturally in the brain. The squid magnetometers are used to measure this magnetic field and thus perform brain activity mapping. This technique is known as MEG. Then the next area of application is the magnetogastrography. In this technique, squid devices are used to record the magnetic fields produced due to electrical activity from the stomach. The third area of application is magnetic marker monitoring or MMM. Squid sensors are used to detect the dosage form of a orally applied drug through the intestinal tract containing a little amount of magnetite, that is Fe3O4, and is magnetized by a high energy magnetic field. Then the fourth area of application is magnetic property measurement systems, that is MPMS. Measurement of magnetic property of the system is the fundamental commercial use of squid sensors. Number 5 application is relaxometry, that is SPMR, NMR and EPR. In these techniques, a sample is placed in the center of the squid detection coils, and by applying the external field or RF excitation to the sample, then corresponding signals are measured. The sixth application is scanning squid microscope, that is by moving a squid sensor across examined area, weak magnetic fields are measured. Then lastly, seventh application is magnetic anomaly detector or MAD. In this technique, squid magnetometers are used to detect infinitesimal deviations in the Earth's magnetic field. The technique is most commonly used by military forces to detect submarines. Now, towards the end, let us discuss the limitations on squid technology. Since the voltage output of a squid loop is a periodic function of the flux, thus, the squid sensors are susceptible only to a relative changes of magnetic field and current. Secondly, the operating point of the squid sensors can shift by one or more flux quanta if the corresponding electronics of the feedback does not follow appropriately to the signal changes, that is, the slew rate is exceeded. This happens when the total signal change exceeds 1 by 2 phi naught. Then thirdly, maximum bandwidth of the squids is approximately half the bias frequency due to the use of AC biasing, which generates 1 by f noise in the sensors. So students, let us now summarize what we have learned in this module. First of all, we learned about the squid, what is a squid and its working principle. Secondly, we learned about the squid sensors, their operation, maintenance and areas. Thirdly, we studied about the type of squid sensors, in which under which category we learned about the different materials, that is the low temperature squid or the high temperature squid devices. Then we studied about the two types of squid devices, that is the RF squid and the direct current or the DC squid. Then we compared the RF and DC squid and saw the plus and the negative points of both the types. Then we studied and we covered all the possible application areas of the squid devices. And in the end, we studied about the limitations on squid technology. Thank you.